Hello, this is Stat135, Lecture 10. Last time we started section 8.5.2, where we discussed some of the asymptotic properties of the MLE estimator. So in particular, if x1 to xn is IID with a given density involving theta, then the MLE estimator is asymptotically normal, unbiased, meaning the mean is theta and variance is 1 over n times the Fisher information. So the Fisher information is the amount of information a single observation x has to estimate the maximum of the log likelihood function. And we saw last time that the Fisher information, it makes sense to define it as the variance of the score function. The score function is the derivative with respect to theta of the log likelihood function. And large Fisher information corresponds to large variance. And that's intuitively information. An observation has a lot of information if the log likelihood for that observation is very pointed. So you are able to quickly identify the maximum of the log likelihood. In other words, the slope at the max there, as we look at different trajectories for different single observations, we see quite a wide range of different slopes. Some will be quite steep facing up, some will be almost flat or flat, some will be quite steep facing down. So the variance of the score will be quite wide. We'll have quite a large Fisher information, whereas you can imagine that if the log likelihood was very uninformative, it would be a very shallow curve, and it would be hard to pick out the maximum of theta, and the range of slopes at the maximum, the range of slopes at the true maximum would be quite small. So they would all be slightly increasing, flat, or slightly decreasing. So it would have a small variance, small Fisher information. So what we didn't prove, I think it was a lemma in the book, is that another characterization of the Fisher information is minus the expectation of the curvature of the log likelihood, which is fairly intuitive, and that's going to actually be our working definition. And today what we're going to do is we're going to look at some examples of calculating Fisher information and also computing the confidence interval for theta using our large sample theory. And we'll see that the confidence interval is theta hat plus or minus the alpha over 2 and 1 minus alpha over 2 quantile times the SE, which is square root of 1 over n times Fisher information. We'll also start section 8.7 and introduce the Kramer-Rao inequality. So main points, if x1, xn are random variables with density f given theta, then asymptotically the MLE estimate is normal, unbiased, variance 1 over n I theta. And the Kramer-Rao inequality says that if the estimator is unbiased, then the variance of the ML estimator is greater than or equal to 1 over n times the Fisher information. In other words, 1 over n times Fisher information is a lower bound for variance of your ML estimator for unbiased estimators. So we're not going to prove these facts. They're sketched in the book, but not worth getting into with the tools that we have at this point. So I'll leave that for another course. Instead, we're just going to use these things. Definition: an unbiased estimator whose variance achieves the Cramer-Rao lower bound is called efficient. So from one above, we see that the estimator asymptotically are efficient, because we see here that asymptotically the variance is the Cramer-Rao lower bound. So let's take a look at an example where x is Bernoulli p, in other words binomial 1p, and I have n IID of these. We're going to find the Fisher information, so we'll use our working definition of minus the expectation of the curvature. And so these steps are fairly straightforward, and we get that the Fisher information is 1 over p times 1 minus p. To find the SE, then, we just take 1 over n IP, which turns out to be p1 over n, and then we take the square root of that as the SE. So that was assuming this asymptotic result about ML estimators. Let's actually compute the ML estimator and compute the SE directly. So the ML estimator we can compute here. X1 to Xn is Bernoulli p. So with our choice of with our given data, we get a likelihood function, and we find that the ML estimator is the sample mean. So that completely makes sense, I think. Now notice that the sample mean is approximately normal by CLT, so that's consistent with the asymptotic result that we have. And also we know that X bar is unbiased, so that's also consistent. Now to find the SE, we can compute the variance, and we see that it is P1 minus P over N. So the SE is the square root of that. And so this actually is the CR lower bound. So everything is consistent with the theory that we gave above. And we can also give the CI once we approximate the SE. So we'll approximate the SE by substituting for p hat, which is just X bar. So our confidence interval will be sample mean plus or minus alpha over 2 and 1 minus alpha over 2 quantile times square root of X bar times 1 minus X bar over N. Now, information on a random sample. I'm going to denote that by I sub n theta. So now now I'm determining what is the information that I get from not just one observation, but n independent observations. So the punchline is, well, you're just going to get exactly n times the Fisher information of a single observation, and that makes sense. If you look at all the steps in this argument here, I'm starting with the definition of Fisher information as a variance, and using using the fact that they're independent log likelihoods, so I can distribute the variance, and it gives me the result right away. So this is not a surprising result, but it actually makes some calculations a little bit easier, as we'll see now. So just to note, we can say now that the MLE estimator is asymptotically normal, unbiased, 1 over sample Fisher information for variance. So let x1 to xn be random sample with density given here, and let's find the MLE estimator, sample Fisher information, distribution for the MLE estimator asymptotically, and approximate the confidence interval. So we compute the ML estimator as usual here. So notice now that my likelihood function, my log likelihood function, which is this, right? So my log likelihood function now, it's more complicated than with a single observation, but that is the curve that I have that I'm finding the maximum with respect to theta. And so to find the Fisher information, I'm using my working definition here. So I'm finding the sample one. So all I have to do is take the second derivative of the first derivative of the log likelihood function, and because the first derivative was the second derivative here doesn't have an x in it. So when I take the expectation, it's the expectation of a constant. So it is just n over theta squared. And furthermore, the ML estimate is approximately normal, theta 1 over I n theta, which is approximately n theta hat, and then the variance is theta hat squared over n. And then I can find my confidence interval using my formula here, and that's the show. So I hope you guys have a great weekend.